I'm looking at period 3 transition metals. First thing you have to distinguish is who are not transition metals, beginning and the end of that period, meaning scandium and zinc are not considered transition metals. They're only D block. By definition, you should have at least one oxidation state with partially filled De electrons. Now, scandium only produces one oxidation state, 3+, and that's 4s03d0, no partially filled d orbitals. Zinc only produces Zn2+ as oxidation state, and 4s is lost before you can touch 3d, and there is no partially filled d orbitals in that. The rest are transition metals. I also put the two anomalies of chromium and copper in red for you to remember one more time. Those are the only two cases that 4s is not filled completely. In case of chromium, it prefers half-filled d orbitals, more stable. In case of copper, it prefers totally or completely filled d orbitals. Then next thing I want to do, so these are valence electrons that I have written. It's you have argon, then you have 4s, you fill it up according to aufbau, then you go after 3d. The four properties of transition metals that you should know and defend and justify is, first is they have variable oxidation states, they form complex ions, they form colored compounds, and they are great catalysts. Now let's look at each one of them. The first one, variable oxidation state. Then again, realize these are all your valence electrons. Technically, you can lose all of them. Now I have put the most common oxidation states in bold. First thing you have to also remember is, this is very important, transition metals lose their 4s before they go after 3d electrons. So they all show +2. So all transition metals have +2. Up to manganese, from titanium to manganese, there is an increase. Manganese shows the highest oxidation state possible, +7. Then there is a decline and you show +2 more often. Now copper, on the other hand, is also only transition metal that has +1 to offer as oxidation state. The higher your oxidation state, the more covalent you are. The lower your oxidation state, the more ionic you are. So if we challenge you and give you valence electrons, make sure you know that you can lose all of them, but +2 first, and then go after each one of them, and you can form different compounds with variable oxidation numbers. So the first property is oxidation number is variable, and that's crucial in other properties as well. The second property is you form something known as complex ion. It's not a compound, it's not an ion, it's combination of two species. The first one is a transition metal, that's the central, and then it's surrounded by ligands. Now the transition metals have high charge density, meaning they are positively charged. Of course, they are metal, positively charged, and very small. They also have partially filled d orbitals and attract lone pair of electrons from ligands to form coordinate bond, covalent bond, or dative bond. So new terminology, it's not a permanent covalent, it's coordinate covalent. Now what are ligands? Ligands you should also be able to define. They are either neutral molecules such as H2O, which has two lone pairs of electrons, or ammonia. They are neutral molecules, or anions with lone pair or non-bonding pair of electrons. Then again, this is extremely important for IB. You have to say lone pair or non-bonding pair. Hydroxide, for example, has 3 non-bonding pairs. Hydroxide is minus, cyanide is minus, chloride is minus. These are all anions with lone pair of electrons. It's also known as Lewis base. A ligand and Lewis base have the same definition. They are electron pair donors. Now, as an example of complex ions, I have picked copper. If you take copper sulfate and you put it in water, it's going to be surrounded by 6 ligands. So I'm going to put arrows like this to say you have H2O. Now the arrow is known as your coordinate covalent or dative bond, and it's pointing to the positive metal ion. Then you will have Instead of H2O, sometimes I write it as OH2. I just want my oxygens to be in front of copper, H2O. Then we usually put it in a bracket and put the overall charge, in this case is 2+. I want to talk about this a little bit. Now the shape, if you have 6 species surrounding you, you have to remember it's spherical sort of. This is octahedral. Now, what is the charge of 2+? It really belongs to copper because H2Os are neutral molecule. So you have 6 molecules that do not contribute anything to the charges, so the 2+ belongs to copper. It's a transition metal. Now what happens is you can also swap sort of ligands. A more powerful ligand can swap a less powerful one. In this case, if I go to the left and if I add hydrochloric acid, HCl, 4 of them, to CuH2O6 complex, I'm going to replace H2O with chlorides. And I'm going to have copper with 4 chlorides surrounding it in a shape known as tetrahedral. So if you have 4 attachments, you could be tetrahedral. We put it in bracket. Now the question is, why am I 2-? Remember, each chloride is 1-, so you have 1, 2, 3, 4 minuses. So copper in this case should be 2+, 2+ plus 4-, you get overall charge of 2-. Be able to do this sort of transactions of positive and negative charges. This is tetrahedral shape of the complex, and your color is also different. We talk about color eventually, but this is blue. This will be yellow. Now if you swap H2Os with ammonia, if you go this way and add ammonium hydroxide, for example, you will have copper surrounded by ammonia. Now I'm going to ignore H2O to give you another possibility of a shape for 4 attachments known as square planar. You're a flat complex, ammonia, 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 ammonia. Put it in a bracket. 2+ makes sense. That's the charge of copper because ammonias are neutral molecule. Now this is square planar. And the color for this is deep blue or close to indigo, and we are going to talk about color now. So you can form complex ions by having a transition metal ion and ligands. Ligands are neutral molecules or ions that have a lone pair of electrons. And the bond that you formed, remember these bonds with arrow pointing to the transition metals, are known as dative bonds. The next property, which is extremely difficult for me to teach and difficult for students to realize, is they form colored compounds, and color of chemistry or paint comes from this notion. Now, if the transition metal atom is isolated, meaning if there are no ligands in that vicinity, remember d orbitals, d sublevel has 5 orbitals. So you have 1, 2, 3, 4, 5. If this is your energy, remember 1s, 2s, and we are going up and up. This is your 3D. They're all staying at the same energy, and this is known as degenerate. They have the same energy. Now, once ligands start approaching this, ligands have lone pair of electrons, and these are negative regions of space. They create an electric field, and they start repelling them. And what happens to the isolated, degenerated orbitals? They will break into 2 distinct energy levels. 3d orbitals stay down here, and 2 of them go up there. Now there is a distance by energy, and now if you have, and this is very important, if you have partially filled d orbitals, if you're completely empty or completely filled up, there is no electron transition. But if you have 1 or 2 or just even up to 9, if you have partially filled d orbitals, white light can come through and the electron can get excited and go up, and then there is some of white light that gets transmitted. So the color that you see is the color that has not been absorbed. So for that, I want to give you an example of titanium 3+. It's purple, and the question is, why is it purple? Now remember, titanium is argon 4s2 3d2. Titanium 3+ is simply argon, 4s is lost, 0, and 3d1. So you have one electron. Now when titanium is isolated, you have 5 d orbitals, 1, 2, 3, 4, 5, and you have one electron sitting in it. So I put just in one of the orbitals, I put one electron. When the ligand approach you, you're going to split into 2 energy levels. Now the electron is sitting here. Now white light comes through, so I'm going to say this is white light. White light. Now remember, white light has all the frequencies or all the colors. You have red, you have orange, you have yellow, you have green, you have blue, you have indigo, and you have violet. Now what happens is some of this light, actually red, orange, yellow, and green, are sort of absorbed, and this electron gets excited and comes up here, excited. So I'm going to show it here and say now the electron goes up here. So there was some energy that was absorbed to get this electron excited, go up there. What you see is the leftover, which is blue, indigo, and violet. This is what's transmitted. And you see a collection of purple light because now you have a mixture of 3 colors, so this becomes overall purple. So what happens is when you have a test tube and a complex ion in it, some of white light is absorbed and the complementary and the leftover is what you see. So absorbance and then versus transmitted. Transmitted is what you see. Why is some of the light is absorbed? In order to get the electron transmitted or excited to a higher energy state. Now, the color of the complex ion depends on a few factors, and when we give you 2 molecules, you just look at it carefully and it comes easy to you. The first one is identity of the central element. Look at nickel surrounded by H2O ligands and copper. They are both 2+, so copper and nickel have 2 different colors. One is blue, one is green. The charge density is important. If you're surrounded by ammonia versus water, I don't think I have that example here, but if I give you example, for example, Cu surrounded by NH3, 2+, this is deep blue. But if you have Cu surrounded by H2O, which doesn't have enough splitting power, you become light blue. Oxidation number is important. Then again, you can look at some of these examples, but for example, Fe2+ is green and Fe3+ is brown. Shape of the complex ion is important. There are a few shapes that you should know. If the transition metal, so let it be M for transition central ion. If it's Mn+, if you're surrounded by 6 ligands, for ligand I'm going to put L with 2 dots. It has a lone pair of electrons to donate. If you're surrounded by this, you have 1 color. If you're surrounded by 4 of them, if you're tetrahedral, you will have another color to offer because of the electric field that is being produced by the shape itself. So then again, you look at the shape and you make a judgment. These are usually to just distinguish why do you have different colors. The last property, which is extremely important, is transition metals are great catalysts, and you need to know many examples and their reactions. Now, what is a catalyst? It speeds up a reaction by offering a new pathway with lower activation energy. If I give you an energy diagram, this is reaction profile or reaction time or coordinate. If, for example, you have your reactants here and products here, usually there is a hump that you need to overcome, and that's known as activation energy. The minimum energy you need for a reaction to take place, this is activation energy. Now, if I offer a catalyst, it will give you a new pathway with lower activation energy. So this is with catalyst. Now, there are two kinds of catalyst. One is homogeneous catalyst, which is catalyst and reactants are in the same phase. The other one is heterogeneous catalyst. Usually have a metal surface, and then reactants are absorbed on it. This is not a misspelled word. If this is my sort of a surface of a catalyst, then again you have a bunch of grooves and valleys. And if I have, for example, two reactants, hydrogen gas, for example, and iodine gas, what they do is they come and they will form sort of a new bonds here. Their old bonds are weakened, and then they form new products. So you will have hydrogen iodides coming to life. Now, this is an extremely brief description. So it's adsorption. They get adsorbed. The old bonds are weakened, the new bonds are formed, and the reaction has been faster. Now, these are what you need to remember. It's annoying, but with practice you might remember it. The first one is extremely important. We will come back to it again and again. Haber process, after Fritz Haber, German scientist, who made production of ammonia a commercial one, and 2 billion people are alive because of that. So this is reaction for production of ammonia. It's very slow and it's also reversible. He said if you put, and he tested it, iron solid, the reaction speeds up. So iron is a catalyst we used here, and you might say iron powder. It's solid form, it's heterogeneous. Another example of heterogeneous is known as contact, not after a scientist, but the way they make contact with this solid catalyst. And this is intermediate step of production of sulfuric acid. Sulfur dioxide is trying to react with oxygen to give you sulfur trioxide. Reaction is slow, so we put vanadium 5 oxide, solid, and the reaction goes faster. Hydrogenation of unsaturated alkene is important. Example, how do we make margarine from vegetable oil? If I take an unsaturated, meaning if you have a double bond here, this is ethene, for example. We mix it with hydrogen, the reaction goes very slow. As soon as you introduce a catalyst such as nickel solid, the reaction speeds up and you will make a saturated alkane. Now, saturated alkane has more degree of packing and van der Waals forces, therefore it solidifies. The next one, which is extremely important, every car has catalytic converter, and it's to convert carbon monoxide and nitrogen monoxide, to poisonous pollutant, into less dangerous ones. So carbon monoxide gas plus nitrogen monoxide. Now this either has platinum or palladium as the catalyst. They're both solid, and it will give you CO2 gas plus N2 gas. CO2 is global warming gas, but doesn't have the poisonous effect of carbon monoxide. Decomposition of hydrogen peroxide. Anything usually catalyzes this, but for sake of your period 4 transition metals, we want you to remember MnO2 solid. It will give you water plus 1/2 oxygen. gas. Now the last two you just have to remember. I cannot write the equation. One, these are homogeneous catalyst examples. One is Fe2 plus in your hemoglobin, my hemoglobin, used to help transport of oxygen. They make a weak bonds with oxygen and they take it from here to there, different cells. The other one is cobalt 3 plus in vitamin B12 complex. Now B12 is needed for nervous system, your red blood cells, so you should just remember these two.